Chapter 4: Zero-Error Data Compression. In this chapter, we give an answer to the question why the entropy of X measures the amount of information in a random variable X. We take a first look at data compression by studying a class of codes called prefix codes. We will discuss how to construct optimal prefix codes called Huffman codes. In section 4.1, we will discuss why entropy is a fundamental bound for data compression. Definition 4.1. A DRE source code C for a source random variable X is a mapping from script X, the alphabet of X, to D star, the set of all finite-length sequences of symbols taken from a DRE code alphabet. In other words, a source code C maps an outcome of the source random variable X to a DRE sequence of finite length. Definition 4.2. A code is uniquely decodable if for any finite source sequence, the sequence of code symbols corresponding to this source sequence is different from the sequence of code symbols corresponding to any other finite source sequence. In other words, a uniquely decodable code does not map two different finite source sequences to the same code sequence. Here is an example. We let the alphabet be A, B, C, and D. Now we consider the code defined by the following table. For the source symbol A, the code maps it to the sequence 0. For the source symbol B, the code maps it to 1. And for source symbol C, the code maps it to 0, 1. And for source symbol D, the code maps it to 1, 0. Then AAD would be mapped to 0, 0, 1, 0, because A maps to 0, A maps to 0, D maps to 1, 0. So AAD maps to 0, 0, 1, 0. Likewise, ACA would be mapped to 0, 0, 1, 0, and AABA also is mapped to 0, 0, 1, 0. Therefore, this code C is not uniquely decodable because it maps three different source sequences into the same code sequence. In other words, from the code sequence, it may not be possible to recover the source sequence. Theorem 4.4 is the Kraft inequality, which is a fundamental characterization of a uniquely decodable code. Let C be a DRE source code, and let L1, L2 up to Lm be the lengths of the code words. If C is uniquely decodable, then summation d to the power minus Lk for k equals 1 up to m is less than or equal to 1. Example 4.5. In this example, we illustrate a technique to be used in the proof of Theorem 4.4. Let L1 and L2 be 1, and L3 and L4 be 2. These are the lengths of the code words in C. Now consider the polynomial summation 2 to the power minus Lk, where in this case d is equal to 2, for k equals 1 up to 4, because there are 4 code words. So the polynomial is equal to 2 to the power minus 1 plus 2 to the power minus 1 plus 2 to the power minus 2 plus 2 to the power minus 2, and we consider raising this polynomial to the nth power. For n equals 2, we have this polynomial multiplied by itself. and we get 4 times 2 to the power minus 2 plus 8 times 2 to the power minus 3 and 4 times 2 to the power minus 4. Where this coefficient 4 for 2 to the power minus 2 comes from the product of this and this, the product of this and this, the product of this and this, and the product of this and this. We are going to call these coefficients A2, A3, and A4, respectively. Namely, A2 is equal to 4, A3 is equal to 8, and A4 is equal to 4. Then, A2 equals 4 is the total number of sequences of 2 code words with the total length of 2 code symbols. Specifically, the 4 sequences are 00 for the source sequence AA, 01 for the source sequence AB, 10 for the source sequence BA, and 11 for the source sequence BB. This is so because when we multiply 2 to the power minus 1 to 2 to the power minus 1, we are concatenating the length 1 and the length 1 to the length 2. Similarly, A3 equals 8 and A4 equals 4 are the total number of sequences of 2 code words with a total length of 3 and 4 code symbols respectively. As an exercise, verify that A3 is equal to 8 and list the 8 sequences of 2 code words with a total length of 3 code symbols. We now prove the Kraft inequality. Without loss of generality, assume that the code word lengths are indexed according to the ascending order. Let n be an arbitrary positive integer. Keep in mind that n is the length of the source sequence, and consider the polynomial summation d to the power minus lk, k from 1 up to n, to the nth power. Writing this out, it becomes summation k1 equals 1 up to m, summation k2 equals 1 up to m, all the way to summation kn equals 1 up to m, where k1, k2 up to kn are dummy variables. D to the power minus lk1 plus lk2 all the way to lkn. By collecting terms of the same degree on the right-hand side, we write summation ai d to the power minus I from 1 up to n times lm, where lm is the largest code word length. Where ai is the coefficient of d to the power minus I on the left-hand side. Now, observe that AI gives the total number of sequences of n code words with a total length of I code symbols. This has been discussed in example 4.5 just a moment ago. Since the code is uniquely decodable, these code sequences must be distinct, and therefore, AI is less than or equal to d to the power I, because there are d to the power I distinct sequences of I code symbols. Substituting 3 into 2, we have the nth power of the polynomial less than or equal to summation I from 1 up to n times lm d to the power I times d to the power minus I, which is equal to 1, and the summation is equal to n times lm. Taking the nth root on both sides, we obtain the polynomial less than or equal to n times lm to the power 1 over n. Since this inequality holds for any n, recall that n is the length of the source sequence. Upon letting n goes to infinity, the right-hand side tends to 1, and we have obtained the Kraft inequality. We now discuss the expected length of a code. Let the distribution of the source random variable be P1, P2 up to Pm. The expected length of a code C is denoted by L, which is defined by summation Pi Li over all I. Intuitively, for uniquely decodable code C, the entropy of x with the base of the logarithm taken to be d is less than or equal to L, because from the code word, the random variable x can be recovered, and each theory symbol can carry at most 1 bit of information. This will be made precise in the next theorem. Theorem 4.6 is the entropy bound. Let C be a theory uniquely decodable code for a source random variable x with entropy hd of x. Then the expected length of C is lower bounded by hd of x. That is, L is greater than or equal to hd of x. This lower bound is tight if and only if Li is equal to minus log d pi for all I. Let us now prove the entropy bound. First, since C is uniquely decodable, the lengths of its code words satisfy the Kraft inequality. Write L equals summation I pi Li. For Li, we write it as log d to the power Li. By taking the logarithm of d to the power Li in the base d, we get back Li. And recall that hd of x is equal to minus summation I pi log d pi. Then, L minus hd of x is equal to summation I pi log d pi plus log d to the power Li. Now log d pi plus log d to the power Li becomes log d pi di to the power Li. Now change the logarithm in the base d to the natural logarithm by multiplying natural log d to the power minus 1. By the fundamental inequality log a greater than or equal to 1 minus 1 over a, with a equals pi d to the power Li, we have log of pi d to the power Li greater than or equal to 1 minus 1 over pi d to the power Li. This pi and this pi cancel with each other, and so we get pi minus d to the power minus Li. Then we can write the summation as summation I pi minus summation I d to the power minus Li, where summation I pi is equal to 1, and summation I d to the power minus Li, but the Kraft inequality is less than or equal to 1, so we obtain greater than or equal to log d to the power minus 1, 1 minus 1, which is equal to 0. This proves the entropy bound. Now, in order for this bound to be tight, the inequality in both 2 and 3 have to be tight simultaneously. Now, 2 is tight if and only if pi d to the power li is equal to 1, or li is equal to minus log d pi for all I. If this holds, we have summation I d to the power minus li equals summation I d to the power log d pi, because li is equal to minus log d pi. D to the power log d pi is equal to pi, and so we have summation I pi equals 1. So we get summation I d to the power minus li equals 1. That is, the inequality in 3 is also tight. This completes the proof of the theorem. As a corollary of the entropy bound, we now give an alternative proof of theorem 2.43, which says that the entropy of x is less than or equal to the log of the size of the alphabet x. We let the alphabet x be 0, 1 up to the size of x minus 1. Let C be the identity code. That is, it maps a source symbol to itself. Evidently, C is an auxiliary uniquely decodable code with expected length equals 1. By the entropy bound, we have L, which is equal to 1, is greater than or equal to entropy of x in the base the size of the alphabet x. Leaving the base of the logarithm unspecified, we have the entropy of x less than or equal to the log of the size of the alphabet, recovering theorem 2.43. We end this section with a definition. The redundancy R of a DRE uniquely decodable code is the difference between the expected length of the code and the entropy of the source. By the entropy bound, we immediately have R equals L minus HD of x is greater than or equal to 0. That is, the redundancy of a code is always non-negative.